So I wanted to talk to you a little bit today about Beamer, which is a lightweight replication tool for SQLite. So what we're going to cover today is, we'll start by doing just a quick review of what database replication does, why it's a useful thing to have. But then for the bulk of the talk, I thought it'd be interesting if we actually look under the hood to see how Beamer works. And the way we're going to approach that is by setting ourselves the task of building a replication system from scratch. We kind of work through all of the points that we need to solve in order to do that. And by the time we get to the end of it, we'll have figured out how Beamer works. And then at the end, we'll just take a couple of minutes to look at what it's like to use Beamer in your Rails application and your McConnell deployments. So database replication, for anyone's not familiar with it, is just a way to have multiple copies of your databases spread out over multiple machines. And those copies are live in the sense that changes that you make to one copy will be visible in the other copies, and you can access all of these copies to run queries and do work. Database replication is often deployed in a setup where for each database you'll have one writable version called the primary and then multiple read-only versions called replicas. It's not the only way to do replication, but it's a very common one. And so for the point of view of this talk, this is the kind of replication that we have in mind that we'll be talking about. As for why this is useful, I think there's really three main reasons. One is just that it helps you avoid having single points of failure in your infrastructure, because obviously if you have all of your database data on a single machine, it's going to be a bit of a liability if anything happens to that machine. So replication gives you a way to spread that out and build in some redundancy. Second reason that replication would be useful is you can then start horizontally scaling your database operations across all of the machines that you're replicating to. And this is useful even in the type of replication we're talking about where your replicas will be read-only, because so many applications do a lot more read work than they do write work. Using Basecamp 4 as an example, I think we often average something like 94% read requests and only 6% writes, which is not an unusual ratio to have in a web application. So if you're in a situation like that, you can see how having lots of even read-only copies means now you can add a lot more capacity to handle those reads. And by moving your reads to the read replicas, you also free up write capacity on your primary to do more writes there. And then the third reason that I think replication is useful to have is it's a pattern that allows you to isolate disruptive actions to machines that are not serving customer traffic. So an example of this would be if you have some heavy data analysis that you need to do and you suspect that these queries you're going to run will slow down everything that's on the machine that you do them on. You don't want to be doing that on a machine that's also serving customer traffic. But if you have replication, you can just replicate your data onto a separate machine and do the work there, and then it will be kind of as isolated. I did want to also mention just a little bit of context of why I went down this replication rabbit hole and started to look at this. Although from David's keynote this morning, you probably have a sense of why we're looking at this. But this really came from, we're building this new app at 37 Signals called Fizzy. It's built on top of SQLite. It uses tons and tons of database files. For anyone who went to Mike's talk earlier about active record tenanted, you will know all of the hows and whys of how it uses so many database files. We also want to deploy this application spread out in various places geographically so we can reduce customer latency by moving the data closer to the customers. So there's quite a lot going on there, and we need to be able to find a good way to manage the replication of the data in our SQLite databases across all these machines. And so when looking at a way to do this and also to make it easy, that's what led us to sort of look through some of our options and ultimately to start building Beamer. And we want to make this easy, not just for our case of this app we're building, but obviously for anyone else who wants to build an app with a similar architecture, we hope you can take these pieces and find it easy as well. OK, so now that we know what database replication is for and why it's a useful thing to have, this is the part where we're going to start digging into the nuts and bolts of how Beamer works by trying to build a replication system from scratch. This is also going to involve digging around a bit inside SQLite and talking about how SQLite works. And I did mention that because there's a lot of detail going on there and we don't have very much time, I'm going to kind of speed run some of the SQLite parts. So if some of the things that I say seem a bit wonky at first, bear with me. I think it will all make sense by the time we get to the end. So this is going to be our initial starting description of what replication does. This is going to serve as the spec of what we're going to try and build. So I think at the core of it, a replication system needs to be able to do these three things. You need to be able to capture the changes that happen to a primary database, transmit those over to a replica, and then apply the same changes to the replica. If you can do these three steps reliably, then your replica databases will do everything your primary databases do, and you've essentially implemented replication at that point. So you could picture this a bit like this diagram where you have a primary database, a replica database, and there's this constant stream of changes that flows from the primary to the replica. That's sometimes referred to as a replication log. So as I say, this is our starting spec. This is what we're going to try and build, but we need a bit more detail in order to do that. And looking at it now, there's a couple of things that stand out to me initially. One is that we're talking here about capturing changes, but change is sort of a vague term. We should probably be a little bit more precise with what we mean there. But since we're dealing with relational databases, the unit of change there is a transaction. So let's start by revising our spec a bit to say that we're actually going to capture the transactions on the primary and then transmit and apply those transactions. The second thing that stands out to me at first with this spec is that steps 1 and 3 here seem like they're doing database-specific tasks, but step 2 doesn't really. Step 2 just sounds like it's sending information from one machine to another machine. And sending data over a network is something that as web developers, we do this all the time. We use HTTP and move data around. We're kind of familiar with this. It seems like a bit of a solved problem. So let's just go ahead and say that we'll use HTTP as the transport for this data, and we can check off point 2 and consider that like we figured out. We know how to do 2, and now we just have the other database-specific parts to solve. Okay, so those were the only 2 sort of obvious easy parts to me on this spec. Now we need to start looking a bit closer under the hood of how things work in order to start figuring out how to do the other parts. So we'll look at how to capture transactions. And the way we're going to solve that involves looking a bit inside SQLite. And the first part we're going to look at is how SQLite stores its data. So logically, the data you work with in SQLite or any relational database is logically tabular, right? Your data is arranged in tables with rows and columns. But that's not how it's actually stored on disk, primarily because if it was stored this way on disk, then a lot of common operations would turn out to be quite awkward and expensive to do. So an example might be if you need to insert a row near the start of a table. If it's laid out in this format on disk, then suddenly you've got to move everything else down to make space for that new row. And in the worst case, you're going to end up essentially rewriting that entire table just to add a single row, which would be quite slow. So what databases normally do is use some kind of tree structure instead. A tree is really nice for this because you can put your data into nodes and then use pointers between nodes to kind of maintain whatever ordering you want to have in that data. But where you store those nodes on disk doesn't have to match that. So you kind of separate the disk layout from the logical layout of the data. And that's what makes it cheap to do things like insert a new node at the top of a tree because you only have to change the nodes it touches. You don't have to touch any of the rest of the data. So SQLite does this. In SQLite, everything is a tree. So a table is a tree, an index is a tree, because an index is really just a table that has pointers for values. The schema catalog, which is the kind of main list of all of the tables, indexes, and other objects in your database, that's also a tree. So this is how SQLite organizes its data. But when we're dealing with trees that need to persist to disk, one trade-off that we have to be conscious of is that the size of the nodes in our tree is going to be important in terms of performance. In particular, if we make those nodes really small, then every time we need to do something to work with that tree that involves fetching a node or saving a node, we're going to be doing tiny little disk operations and lots of them, which will end up being quite inefficient. There's a bit of an overhead for every I/O operation you do, and disks work a lot more, or perform a lot better if you can batch that work up and kind of write chunks at a time. So the way SQLite deals with this is that all its trees are built out of these fixed size blocks called pages. By default, they're 4K, and they'll always be the same size within a single database. So we'll assume just the default for now, they're always 4K blocks. That means that the pages can contain data for multiple rows as well as the pointers to the other pages in order to kind of form the tree structure. Then the SQLite data file is literally just all of those 4K pages written out in their page number order in a file. That's the file format of a SQLite database. And then whenever SQLite needs to read and write any changes to the data, it's always working on pages. So it's always doing these like 4K reads, 4K writes kind of thing. Okay, I know we're getting in the weeds a bit here, but knowing this, we can start making our first revision to this spec to get more detail in there. And now we'll just note that when we say we're going to capture transactions for a primary, what we're probably going to do is capture these changed pages because that's how SQLite works with them. So at least now we have a little bit of a notion of the file format of the data that we're dealing with. But what we don't know yet is how do we find which of the pages are the changed pages whenever there's a transaction. So we'll continue poking around in SQLite, and we can find the answer to that. This time looking more at how SQLite updates data when it changes. So we just said that the read and writes always happen as whole pages, and we also said that SQLite's data file is just these pages laid out on disk, one after the other in their order. So when it comes time to persist a change to disk, the simplest possible thing SQLite could do would just be write the new version of the pages directly into that file whenever they happen. And that would work fine if you are the only process accessing the database at that time, but very often you're not. Often there'll be lots of processes and threads, maybe different Puma workers or something, that are all accessing the same database. And so we can't just write changes on top of other pages anytime we want, because we're going to trip up the work that some other process is doing if it's trying to read from a page we're writing to, and so on. So if we can't do this, the very simplest thing, perhaps we can do the next simplest thing, which would be just to add a big lock to this. So anytime we want to write, the process that wants to write could take an exclusive lock on the whole database. Then it can write whatever it wants to whatever pages it needs to change. When it's done, it can release the lock, and then the other processes that want to use the database can continue their work. This actually works fine, and SQLite has a mode of operation that is essentially this. But the downside to this is it's just really bad for concurrency. If you have a lot of processes that all want to do things to the database, but anytime one wants to write, all the others stop, then in practice you'll find a lot of time where only one of your processes is really making any progress on its work, and all the other processes are just kind of waiting on this lock to be released. So to improve on this, SQLite has another mode of operation, which is called wall mode. Wall mode works by adding a second data file alongside the main data file called the wall file, which stands for the write-ahead log. That's where wall mode gets its name. And the wall file is built out of these same fixed-size pages as the main database file, but the wall file is an append-only file. So rather than overwriting anything in it, you're always appending to the end. The way this gets used is that whenever SQLite wants to record a change to a page, it will write it onto the end of that wall file. And then whenever it needs to read in a page from the database, it'll look to see if there is a copy of it in the wall file first. If there is, it can use that. And if it's not in the wall, it will look for the main database file. So another way to think of this is that writing a copy of a page to the end of the wall is effectively shadowing any previous copy you had of that page in the wall or in the main database file. It can't do this forever. You can't just continually append to file, because eventually the wall file will become massive and consume all your disk space. So there's also a periodic task called a checkpoint, which runs when the wall starts to get too big. And the checkpoint will just take the latest version of each of these pages, copy them back up to the main database, and then it can throw the wall away and start over with a new one. So the wall file will sort of periodically rewind. But in between those checkpoints, the point that I'm trying to get at here is that all of the write operations are essentially just append, append, append onto the end of a WAL file. So if you could see it inside, it would probably look like this, I think. Now, WAL mode has a couple of really nice properties that make it work better for concurrent workloads. One of them is that writes don't need to block reads anymore. Since you're not overwriting pages, that means if other processes want to read the database while a write's happening, they can continue to do so, and nothing's going to pull the rug out from under their feet by changing a page they're reading. So that's nice. But from our point of view, as people who are trying to build a replication system, the other reason the WAL mode is nice is that if you look at the WAL file, it's essentially a continuous stream of changes that just happen to your primary database. They're even delineated by transaction. There's little markers in the WAL that tells you where each transaction starts and stops. And this is perfect for what we need, because this tells you all of the changes that just happen to your primary. This starts to look a lot like that replication log on our first diagram. And if we can capture this information and play it back on our replica database, our replica will do whatever the primary did, and essentially we're getting to the point where replication would work. Knowing all that, once again, we can revise our spec with a bit more detail, and just to note that capturing transactions now means that we'll capture the changed pages of each transaction from the WAL. I realized that was a really long digression just to get 3 more words in our description there, but they're important words. They're doing a lot of work there. So at this point, we know quite a bit about what we need to do for step 1 here, but the part we're missing, I think, is the timing related part. We know what format of data we're capturing, we know where we're going to find it, but we don't know how do we know when there is a new transaction ready to be captured, if you see what I mean. We need the time aspect of this. So once again, we'll go looking at SQLite for this. But this time we're taking kind of a high-level view on SQLite. And this is what its overall architecture looks like. So SQLite's built with a layered architecture where each of the layers does one specific task, and it does that by using the services of the layer below it. So code that you write or active record or whatever will interact at the top level with this interface. It can send in SQL commands, which go to the SQL command processor, where they'll be parsed out. An execution plan is devised, and they get turned into bytecode, which runs on a virtual machine. That virtual machine carries out that program by manipulating the trees we were looking at earlier, using a layer called the B tree. And the B tree is going to need to read and write those 4K pages we looked at earlier, which it does with a layer called the pager. The pager is going to need to work with files on disk for this, but it doesn't talk directly to the operating system to do this. Instead, it goes to this last layer at the bottom called the virtual file system, or VFS. The VFS exists mainly for portability. It's one of the reasons that SQLite is quite easy to port to different operating systems and platforms, because if you make a VFS for your operating system, then all these other layers can operate on top of it, and all of SQLite can run there. The other interesting thing about the virtual file system is that in addition to the built-in one, so SQLite has a virtual file system for Windows and for Unix and so on, but you can also build your own, and you can load in new ones at runtime and tell SQLite to use them. So essentially, the top 5 layers of this diagram are all hardwired together, but the bottom part is pluggable. And because the bottom part is pluggable, and because you can write your own, you can also do a neat thing where you can wrap a file system with another file system. And when you do this, SQLite calls this a VFS shim. And so a VFS shim is a way that you can get your own code into this stack, and your own code can be involved in the interaction between the pager and the virtual file system. But you don't have to build a whole file system to do it. You can just delegate the work to the file system below it. Okay. So that's good news for us, particularly because one of the things that happens at that level is that whenever the pager records a new transaction to the database and commits it and records it into the wall, it fires a particular event into the virtual file system to let it know that that happened. So the reason that's good for us is because it gives us the last piece of information we need to figure out how to implement step 1 of our replication, which is that if we implement a VFS shim, we'll be able to intercept the commits, capture those change pages out of the wall for every transaction as it happens. Then we can transmit those to the replicas over HTTP. And now we just need to figure out how to do the step on the replica, part 3. So figuring out part 3 also requires going back into SQLite, but I will say part 3 is way easier than part 1, so this one won't take nearly as long to sort out. So looking back at this architecture diagram, the transaction data that we captured out the wall was those pages. It's pager-level data. And that's what we want to apply on the replicas. But normally when we work with SQLite, we're dealing with things up at this interface level. We don't want to be going through all these layers again on the replica, because all that work already happened before we captured the transaction. What we really need is a way to just skip over that. As luck would have it, SQLite has a thing that lets you do exactly that and skip over it. So SQLite has a virtual table called SQLite-DB page. And SQLite-DB page is not really a table. It's actually the pager masquerading as a table. So if you select out of SQLite-DB page, it will return the raw 4K binary chunks of each page to you. You get back rows where you have a page number, and you have that binary data for the page. Even better than that, you can write to SQLite-DB page. So if you insert into it, you can pass in a page number, a 4K chunk of data, and the pager will go and write that into the database just as if it had come from all the layers above normally. And because the pager, as we said, was that part that's responsible for transaction safety and concurrency safety, then it will do this in a way where you can feed data into it like this while other people are reading the database, and it will make sure that that all happens in a kind of controlled and safe way. So that turned out to be the only thing we needed to do for step 3. This now gives us the whole picture and kind of a detailed enough spec that we could go off and build this, and this would be the replication flow that would manage changes from a primary database to a replica database, and it's exactly the way Beamer does it. I should add, though, that all this part that we've been discussing is kind of that core replication flow, like I said. So it's the main thing you need to do if you want to replicate your databases, but it's not the only thing you need in order to have like a system that you can set up and work with and operate and kind of is easy to use. There's a bunch of other plumbing you're going to need. So Beamer does add kind of a number of other things to make that easier. But it's all really built around this kind of central idea of shipping changes. Hopefully that makes sense. OK, so that kind of covers, or we have covered what database replication's for, why it's a useful thing to have. Now we know how Beamer does it, or how to build it yourself if you want to build your own. So the only other thing that I wanted to talk about at the end was just what it looks like to use Beamer in your applications. Getting Beamer into your application has really two parts. One is that we need that VFS to be available so that we can capture the transactions, because that's the part where we implemented that. So for a Rails app, we could just use a gem. Beamer has a gem that when you include that in your app, it'll make sure the VFS is available. And then in your database YAML, you can specify which of your databases you'd like to be replicated and which not, if you don't want to do them all. Second part is that there's a Beamer process that runs on each app server. That process is responsible for things like the network traffic between the nodes and responding to commands that you run and so on. That's a Docker image, so you can just add that to your Kamal deployment as an accessory, and it will run on each of your app nodes. If you do these two things, then Beamer is available, and you can start replicating. At that point, there's several different commands that Beamer provides that you can run to control what the replication's actually doing. Only one of them is really required, and that's you need a way to tell Beamer which of your app servers you would like to act as the primary. So this command, Beamer switch, sets the current primary in a cluster of app servers. When you do this, the machine that you specify to be the primary will allow you to write to the databases there. It will capture the changes and make them available to be replicated to the other machines. All the other machines that are not the primary will follow along with the changes on the databases of that machine. They'll also set their copy of the databases into a read-only mode so that you don't accidentally make a change on a primary when you shouldn't. You can run Beamer switch at any time, so if you need to do a failover, like if app 1 dies or you just want to move your primary somewhere else so you can take app 01 offline, then you can just call Beamer switch again. All these nodes will reconfigure themselves to start replicating in a different direction. And you could obviously automate this as well if you want to put it in something like console so that when a machine dies, it will automatically elect a new one. There are several other Beamer commands as well. We're not going to go through them all in detail, but I just put a few of them up here so you can get a sense of the kinds of things that it can do. And then the other part that I want to talk about in terms of using Beamer is that when you've set up a cluster of machines and you've got replication running between them, and now you have read-only replicas, you're going to want to be able to serve some of your app traffic to them. So to be able to do that, we've added load balancing to Kamal proxy, so it now has the ability to load balance traffic amongst a number of nodes. But it also knows how to split that traffic between reads and writes based on the HTTP method that's in each of those requests. So you can do something like this, where you set up a set of machines which uses Beamer to replicate. So you have one primary in that orange color and a couple of read replicas. And then Kamal proxy will send all of the writes to the primary, and all the reads will be load balanced amongst the other machines there. This kind of setup is also the basis of how you can start doing the thing of moving data nearer to customers to reduce their latency. So the simplest example of that, I think, would be that you can make 2 deployments of your app. You can use some kind of geo-DNS service that will route customers' traffic to the nearest point, depending on where the traffic originates. You could make a main deployment in Europe where you have your primary database and a couple of read replicas, but you can also make like an outpost deployment in the US, which has read replicas there. So then your US customers, their traffic's going to land on that load balancer in the US, and all their read requests will be much faster because they're coming from those read replicas that are in the US and have much less latency. Obviously, in this setup, there's still only one primary, which is in Europe. So the US customers will still be paying the latency to get to Europe whenever they do a write. That might be fine. I mean, if you're an app like Basecamp 4 and 94% of your requests are reads, then just doing this has made 94% of your requests faster, and the other 6% are just the same as they always were. So that's already kind of helpful. But if you do want to get a bit fancier, you can always segment your customers into different writable databases and then start putting those in different places as well. And that way, you can have your US customers live in a database that's in the US, and they'll get faster reads and writes, and same for Europe. And obviously, this can be expanded out to multiple different places. Okay, so the last thing I wanted to leave you with for a wrap-up is just a note on the current status of where the Beamer project is right now. So we're using this internally. It's what powers this new app, Fizzy, that we've been talking about a few times today, which we're planning to release soon. So at the point where Fizzy releases, that's when Beamer will start having kind of real production traffic. So that should be soon. We are still experimenting a little bit with different strategies for how to operate this multi-realm, multi-writer kind of setup like we saw on the last slide. Because you can do it now, but it feels a little bit more complicated to set up than it should be. So we have some ideas about trying to make that dead simple. But in any case, all of this is going to be open source soon. You can try it out for yourself, and if you do, we'd love to hear what you think of it. Thanks very much.